Hi, it's Goof here. We're going to do some Byron Ninja automation with Jupyter. So yeah, let's jump into this. So if we switch over to our notebook, what we're doing here is we're importing some Python modules to help us manage and manipulate Byron Ninja, so extract features that we want from binaries, but also be able to put that data into a pandas data frame, and then be it a CSV file, Parquet file, whatever format we choose, and then manipulate that, do some queries on it, and do some charting visualization. So we can get promoted. But yeah, let's kick this off. So if we go to our cell here, we've got our Byron Ninja script. So we're using the headless API in Byron Ninja. So we're using the commercial version of Byron Ninja, so we can use that headless mode without actually running the GUI version of Byron Ninja. So this unfortunately won't work with the free version or the personal version, but you can do a lot of this stuff with the personal version. You just have to do it within the the Python console, or use snippets, or some of the functionality that's in Sidekick, like the indexer, so you can write your own scripts in there, which is probably a better way of doing it. I don't recommend using the Python console within Byron Ninja for anything more than a few lines long, otherwise you'll get lost quickly. But yeah, so what we're doing here is we're setting up, looking for some potentially dangerous functions. So basically, potentially dangerous calls to system. This is a small subset, so the script doesn't take forever to run. But obviously, you would have a larger data set if you want, to help you with your coverage when searching. We're basically going to iterate over a batch of binaries in a folder and say, hey, give me these, whilst we're looking for these potentially dangerous calls to system, give me the file name of the binary that we're currently looking at, the architecture, the endianness, a file hash for that particular binary, the cyclomatic complexity for that binary, so we'll take an average, and then calculate the entropy for that binary. So that will help us look for things like, is this binary heavily packed? Is someone up to no good? So if we're seeing 7 bits of entropy for every 8, we might want to investigate that further. That might be an indication that I think what they call it in the intelligence community a clue. Yeah, we might want to look at that. And then if we continue, we're looking at the memory segments and whether those are readable, writable, and executable. And then we're just obviously iterating over those dangerous functions and pulling up the respective name and the address for that particular function of interest. And then we take all of that and then stick it into a Parquet file. We could use CSV, but I prefer Parquet because they're smaller files, they're quicker, and they retain the data types, or they'll do their best to retain the data types, whereas CSV files everything's an object, enjoy. So yes, we've run that already in the tradition of here's what I did earlier. Otherwise we'll be here all day. So that's completed. What we'll do is we'll load our Parquet file. So we'll create a data frame from that park over. And as you can see, we have a series of binaries that we've extracted features from. As I said before, we've got the binary, the file hash, the architecture, endianness, average psychometric complexity, the entropy, a list of functions, list of strings, the segments and whether they're readable, writable, executable, and then what we're really here for is a list of potentially vulnerable calls to systems. So sometimes there might be none, sometimes there might be many, but yeah, so we've gone through about is it 16, 17? Oh, okay, 15 binaries. So these are basically all HTTP D binaries for various routes. So these are real world binaries, they're not toy binaries. And then using the power of query, which we get for free with the pandas data frame, we can string together some artisanal SQL statements or search terms and say, hey, for the entropy, give me everything that's greater than 6, and for the endianness, I want only the ones that equal big endian, and then for the average psychometric complexity, give me everything that's greater than 3. So we can then reduce our binaries that we're interested in to a smaller subset. And this is a contrived example, but if this was, say, something malicious and we'd been given indicators of compromise by another organisation or agency, we could say, hey, look for these particular aspects. You might want this specific or specific file hashes, or other attributes. So it's got these particular functions. There are many things we could look for. So use your imagination. And then obviously, as we're doing these searches, we can also look for specific strings, and what we're doing here is make sure that our data types aren't actually strings and aren't some random ints that will cause searches to fail. And then we can go through and say, hey, within the strings column, give me everything that contains this specific address, and then that's returned two entries for that. And then we can go through and do the same thing with functions and the other columns as well. And then we can also use Jupyter to do charting as well. So we can say, hey, let's give me average psychometric complexity that's less than 3.6, and then we can say, we could chart that. That'd be great. Or we could say, how about, I want to know actually how many vulnerable calls are there for these specific binaries, so we can use some lambda and create another column that has that information. And as you can see, some of these have a large number of potentially vulnerable calls. So that's something we'd obviously want to go and check in further detail. But as I mentioned previously, we can also chart. I'm using a pandas bokeh here, or bokeh, depending on how you want to pronounce it, to say, hey, give me an interactive chart, so I can hover over and see how many actual potentially vulnerable calls are there, and then we've obviously sorted that into a you can sort by ascending or descending, however you want to slice and dice the data. And obviously we can do that for entropy and psychometric complexity. Yes. As we've got more interactive charts here. But we can also highlight data in in a tabular form, and also look at things like similarity. So are these what we're using here is a Cisco RV130 router, and we're just going through various revisions of the firmware for that to see, are there similarities between any of these binaries, and would that necessitate further investigation? And as you can see, according to this, and it will take a while to run because there are many permutations, about 70 plus of them, and as you can see, some of them have high similarity, some of them don't. So there are at least 2 that are almost identical. So yes, but there's a flaw with our approach here. So we're just going through and doing a chi-square test against the code and saying, hey, is this similar to this other binary? But what we're not looking at is things that are imported. So say for example libc. So in this instance, you see libc is identical for every binary. So because we're being a bit more specific in what we're searching for, we're missing out on potential findings. So we're trading speed for precision and all that good stuff. So we'll have to look at that and say what's the balance we want to strike, how much automation do we want, how much manual effort do we want, because we can't, we shouldn't rely on one or the other, because that's likely to lead to errors and missing things. So the idea is that we use automation to provide assistance where those things are expensive and laborious for an individual to manage, but if we can focus our efforts down to a smaller subset, a manageable subset of potentially vulnerable things that we want to look at, that's a far more efficient use of our limited time than just saying, hey, we're just gonna blindly run automation against everything, or we're just gonna rely on manual efforts alone. Neither of those standalone approaches are recommended. You have to have a mix. As we see, we've got a little heat map of the Jupyter similarity, and we've also looked at running some pwntools checksec, do a batch scan against those binaries that we looked at before, and say, hey, what protections are actually in place for these binaries? And you'll be shocked to hear there aren't many, which is not uncommon for routers and /IoT devices. Some are better than others, but broadly speaking, we are time traveling back to the 90s with some of the practices here, and that's obviously an artifact of the limitations of the devices, but also relying on some random blob from a vendor. So you're going to have I hope you like issues in your issues, because you can have them. And then just a brief word about Binary Ninja's intermediate language. So using the wonders of compiler theory, we can go through and do many wonderful things like simplifying functions, doing constant folding, all that good stuff. Obviously static single assignment, so we could say, hey, this particular potentially vulnerable core system, is it can we reach that via user controlled input, because we're basically at every stage of execution and every branch we're saying, hey, is this variable argument, how's it changed, who controls that, and obviously work up and down that call graph to confirm that. And as you can see here, we do in fact have a vulnerable call to system. So I would hate to change that that SSID setup there. That would be a shame. And then also we can use things like, hey, is this a medium level intermediate language call, and is it a constant? So we're not just looking for random strings, but we're looking for is this thing called? Yeah, there we go. So here are some references, some useful references for pandas, for doing charting, the Binary Ninja API, and there are some great references for doing further automation. So there's some stuff from Setfile, so John, great videos there, and also have a look at them at your leisure. But I will see you soon. Take care.